Okay, let's jump right in. For, well, centuries, we had this picture of everything circling Earth.
Right, the geocentric model.
Exactly. And trying to map the planets, those wanderers, from that perspective, it made their paths look incredibly complicated almost. Random sometimes.
Absolutely baffling. It took a huge shift in thinking, putting the sun at the center to really start making sense of it all.
That heliocentric view, yeah. Suddenly those wild loops smoothed out into orbits we could actually understand.
But interestingly, even that picture, planets just neatly orbiting the sun, isn't quite the full story, is it?
No, it's more subtle. We tend to imagine the sun as this fixed anchor point.
Uh-huh. But really, everything in a system, the star, the planets, everything is orbiting a common point.
The center of mass. I love the ice skater analogy for this.
Oh, yeah, that's a good one.
Like, if you have two skaters holding hands and spinning, right?
Mm-hmm.
If one's way heavier, it might look like the lighter one is doing all the moving, just spinning around the big guy.
Mm-hmm. But if they're the same weight,
Then you see it clearly. They're both orbiting that empty spot right between them.
that's the barycenter. And even with a huge star and a tiny planet, that point exists. It might be deep inside the star, maybe very close to its center.
But it's not exactly at the center. The star has to move, just a little, around that barycenter too.
And that little becomes, well, pretty significant when you start measuring things with extreme precision.
Especially with big planets, right? Gas giants, their pull is stronger.
Exactly. That barycenter can shift noticeably away from the star's actual center. So the star isn't still, it wobbles, it dances.
Which is honestly super cool because that wobble, that stellar dance,
Hmm.
that's become a key way we find planets around other stars, exoplanets.
It really has. It's a whole field of study.
So that's our mission for this deep dive then. We're going to look at how these gravitational tugs, especially from multiple planets, make the star itself move in these complex patterns.
And crucially, how we can observe that movement from light years away to learn about those unseen worlds.
Okay, so where should we start? Maybe with the person who first really nailed down planetary orbits.
Sounds good. Let's talk about Kepler, Johannes Kepler.
Right. He spent years, didn't he, just obsessively tracking Mars.
Obsessively is the right word, using Tycho Brahe's data, which was the best available then. And in 1609, he published Astronomia Nova.
And the big breakthrough there was,
Ellipses. He realized planets don't move in perfect circles like everyone assumed.
no, they move in these sort of stretched circles, ellipses, with the sun at one of the focus points, not the center.
That's his first law. And his diagram of Mars's orbit, seen from Earth, was remarkably accurate, a huge leap.
Then Newton comes along later and provides the why with gravity.
Exactly, universal gravitation. And Newton himself pointed out that because of this gravity, the sun can't be perfectly stationary either.
Ah, right, because if the planets are pulling on the sun.
The sun has to be pulling on the planets, and it also gets pulled by them. He said the sun must continuously move every way around the system's overall center of gravity, even if it doesn't move far from it.
And we can actually see this with our own sun. There's that plot showing its path from, what, 1970 to 2030?
Yeah, based on the pulls of Jupiter, Saturn, Uranus, and Neptune mostly, the big guys.
And it's not a simple circle at all. It's this loopy, kind of complex path.
It really shows the combined effect. And get this sometimes, over decades, the sun actually moves a distance larger than its own diameter away from that average center point.
Wow. Okay, so it's not just a tiny negligible wobble then.
Not over the long term, no. And this principle, this gravitational tug of war, it applies to any star with planets. It's universal.
So how do we actually spot this happening light years away? It must be incredibly subtle.
It is, but we have a couple of main ways depending on how we're viewing the system.
Okay.
If we're looking at the system sort of edge on, so the planets orbit towards and away from us.
Then the star will also be moving slightly towards and away from us.
Precisely. And that movement causes a Doppler shift in the star's light. Tiny shifts in its spectrum.
Towards the blue end when it moves towards us, red end when it moves away. Like the sound of a siren changing pitch.
Exactly the same principle. We call that the radial velocity method. It's been hugely successful for finding exoplanets.
Okay, so that's edge on. What if we're looking down on this system, like face on?
Then we might be able to directly see the star moving side to side across the sky.
You mean actually tracking its position changing over time, like watching it wobble?
Yes, exactly. Measuring its precise coordinates again and again. That's called astrometry. It's much harder because the movements are minuscule from our distance.
I bet. And Upsilon Andromedae was one of the first places this was actually done, right?
It was a bright star relatively nearby. It was already known to have planets from radial velocity studies.
So they knew something was making it wobble back and forth.
Correct. Then they pointed the Hubble Space Telescope at it. Over 4 years, Hubble took incredibly precise measurements of its position.
Just pinpointing exactly where it was in the sky.
Mm-hmm. And those measurements, the little dots on that diagram people might have seen, allowed astronomers to trace out the star's actual path, that red curve.
And it wasn't a simple ellipse.
No, because there isn't just one planet pulling on it. Multiple planets mean multiple gravitational tugs, all adding up.
Creating a much more complex dance for the star.
A complex dance. If it had just one planet, the star's path would just be a scaled-down version of the planet's elliptical orbit. But with more planets, you get these intricate patterns.
Okay, but doing that kind of astrometry, measuring those tiny shifts,
Yeah.
that must require unbelievable precision. Hubble could do it for a few bright targets, but
But not routinely, and not for vast numbers of stars. That's where Gaia comes in.
the Gaia mission, the game changer.
Absolutely. Launched by the European Space Agency, its whole job is to map the positions and movements of billions of stars with unprecedented accuracy.
Unprecedented is definitely the word. The precision is just mind-boggling.
So the expectation was that by around 2020, Gaia would have maybe 100 or so position measurements for tens of thousands of stars suspected of hosting planets.
30,000 systems, I think, was the number mentioned. That's incredible.
It is. Now, of course, turning that raw data, billions and billions of measurements, into scientifically validated results, like star paths, takes a lot of processing.
Yeah, calibration, checking, cross-referencing.
Yeah.
It's not instant.
Not at all. The timeline was always that the big results related to this kind of astrometric detection of planets would start rolling out around now, 2025.
So we're right on the cusp of potentially seeing thousands of these stellar wobbles mapped out.
Exactly. But even before the final Gaia data drops, scientists could already do something pretty cool.
What's that?
Well, for systems where we already knew about planets, say, from radial velocity or transits, and we had good estimates of the star's mass and the planet's masses and orbits.
You could calculate the wobble.
Yeah.
You could predict the path the star should be taking due to those known planets.
Precisely. You can model the gravitational interactions and plot the star's expected motion over time.
And those predicted paths are the planet mandalas.
That's the evocative name they've been given, and they look amazing.
Yeah, the figures show some examples. HD 69830, 3 planets, just 2 years of predicted motion makes this intricate little loop.
Then you've got HD 155358, 2 planets over 10 years, a much wider, more open pattern.
HIP 14810, HD 4307, both 3 planets, 2 years. Again, these tight, complex little dances.
And then longer predictions. Upsilon Array, 4 planets over 30 years. That looks incredibly complex. And HD 37124, 3 planets, 30 years. Another beautiful looping path.
It really drives home that these systems aren't static. They're constantly evolving dynamic dances.
And the key thing is the shape of that dance, the specific loops and turns the star makes.
Encodes information about the planets causing it, their masses, their orbits, how they interact.
Exactly. So by observing the actual dance with Gaia and comparing it to models, we can potentially confirm known planets, find new ones, and really map out the architecture of these distant systems.
It's like deciphering the choreography to understand the dancers.
A very neat analogy. And there's another effect of this stellar motion, too, related to transits.
Ah, right. Transits are when a planet passes in front of its star, from our point of view, causing a little dip in the star's brightness.
Yes. Now, if a star is wobbling around the barycenter because of other planets in the system,
Then the timing of when that transiting planet crosses the star won't be perfectly regular.
exactly. Imagine the planet is trying to run across a stage, but the stage itself is moving slightly back and forth.
The crossing time will vary a bit each time.
These are called transit timing variations, or TTVs. Missions like Kepler, which stared at stars looking for those brightness dips, observed these variations.
And the cool thing about TTVs
Is that they can reveal the presence of other planets in the system, even ones that don't transit themselves.
because their gravity is the thing causing the star, and thus the transiting planet's path relative to us, to shift slightly.
Correct. By analyzing how the transit times of one planet are varying, you can deduce the gravitational pull of unseen companions, estimate their mass and orbit. It's another indirect detection method born from this barycentric motion.
It's amazing how interconnected it all is. The simple idea of planets orbiting a star blossoms into this complex reality of everything orbiting a common center,
Which makes the star itself move.
which we can detect through Doppler shifts or direct imaging of the wobble or even variations in transit times.
It's a beautiful example of how subtle gravitational effects, once just theoretical, become powerful observational tools with modern technology.
So wrapping this up, the big takeaway is that solar systems aren't just planets circling a static star. They're these intricate gravitational ballets.
Absolutely. Everything orbits the barycenter, including the star. And that stellar motion is key.
And Gaia. Gaia is poised to just open the floodgates on this, right?
Yeah.
Showing us potentially tens of thousands of these stellar dances.
That's the hope. An unprecedented census of planetary system architectures and dynamics revealed by tracking the stars themselves.
It really makes you reconsider our own place, too. Our sun isn't fixed. It's on its own journey around the solar system's barycenter, constantly influenced by Jupiter and the others.
This constant motion, this interconnectedness, it's fundamental.
So maybe the final thought for you listening is, what else might these intricate stellar dances be telling us? Beyond just finding planets, what secrets about how systems form, how they evolve over billions of years, are hidden in the details of those planet mandalas that Gaia is now revealing?
What happens when planets migrate or interact gravitationally? How does that shape the star's path? There's still so much to learn from watching the stars dance.